This example is going to use a much larger data set in order to run a regression, and what we're trying to find here is, given someone's stature and their forearm to hand length, we want to make an estimate as to what their foot length is. So to come up with this regression, we're going to use about 1,800 samples from the answer data that we've used before, but it's a pared down set of it. And using that regression, we then can come up with this formula that will make an estimate in general, that if we know those two values about someone, again, their stature and forearm to hand length, that we can have a pretty good estimate as to what their foot length is. So the first thing I want to do is import my data, which is saved in L07 answer. So if we run this and we load that data in, we have this in our workspace, this variable called data. And the stature, which I'll call ST, is the first column of data. Their forearm to hand length, which I'll call just F, is the second column of data. And their foot length, which I'll call foot, is data, the third column. Let me call this FA for forearm to arm. Or forearm to hand length. That way we don't confuse this quite as much. And then I can get rid of that variable data once I take everything I need out of it. So if I run this, I take stature as the first column, forearm hand length as the second column, and foot length as the third column. And then I just get rid of that matrix called data because I'm not going to need it for further analysis. Alright, so first thing I want to look at is, what does my raw data look like? I have what I'm going to call two independent measurements, the stature and the forearm hand length, and then one dependent that I'm going to try to find the relationship for, this foot. Alright, so I'm going to use scatter 3 since I do have three-dimensional data here in order to observe this data. And I'm going to add some labels here so I know what's happening. So this is stature in millimeters in the X. Y is forearm hand length. And my Z is the foot length. And again, all of these are measured in millimeters. Alright, so I get this cloud of data out of it. So again, I have three measurements I'm making. I'm trying to find, if I only know stature and forearm length, I want to make my best estimate as to what someone's foot length is. So from these 1,800 or so observations, I see that this data cloud, and we see that it does have kind of this elongated shape here. And the general trend would say that if the larger someone's stature and the larger someone's forearm length is, that the larger their foot length is. And intuitively this makes sense, but we want to find a more exact relationship. That's the general trend that this data cloud is showing us, that all three of them measure vary basically together. So when two increase, the other one increases as well. So the next step is assembling that A matrix, and here I'm going to include a constant term, and we'll see how that is going to affect our results in the end. So I need to assemble that A matrix. Now one way I can do it, I'll start without using a constant, is I can take the stature and the forearm hand length and put those together to form A. So we see here we have our two independent variables, with the first column being the stature and the second column being the forearm hand length, just like we saw before. But in this case we have 1,774 observations. And B is going to be my foot length. So what I can do here is I want to find, without using a constant term yet, the relationship between what do I have to multiply my stature by, and then what do I have to multiply my forearm hand length by in order to make an estimate as to the foot length. So if I just run this, I get these as my x values, 0.0538 and 0.3619. So this says that I can make an estimate as to someone's foot length if I take their stature times 0.0538 plus their forearm hand length times 0.3619. But this isn't a very good estimation here. I can make it better by also adding a constant term here. So what I want to do is in this A matrix, I have my stature data, my forearm hand length data, and now I also want a column just of ones. So this will represent the constant term that I'm going to be adding. So it needs to be the same length as either stature or forearm hand length. It doesn't really matter. So again, I've added that third column onto A, which is going to represent constant terms. So what's going to happen? Now for my X, I'm going to have 3 values in it. So now this is saying, once I run this regression again with this A matrix with that extra column of ones, that my best plane that passes through all of my data points is 0.0434 times stature plus 0.359 times forearm hand length plus 19.77. And then that gives me my best estimate as to someone's foot length. So I have the equation here, or at least I have it saved in X. Now what I can do is use this. Let me clear my screen. I can use this to make estimates. So if I have someone who wasn't part of this original 1774 measurements, and someone who's only the stature and forearm hand length I know, I want to be able to make an estimate as to their foot length. So in this case, I have someone who's 1800 millimeters or 1.8 meters tall and has a hand length of 480. And I'm going to use this information to estimate what their foot length is. So in this case, because I did add that constant term at the end, for this person, they're going to have data of 1800, 480, and 1. And I can multiply this now by X. And if I run just that line, using my regression, I've come up with an estimate of their foot length of about 270 millimeters. I'll call this foot E for foot estimate. And let me add that to the data cloud, just this point. So again, their X value is 1800, their Y value is 480, and now the Z value is 270, but it's also stored as foot E. I'm going to add this, and I'll do this as a red star so that I can see it. So find foot E first. Rerun this all. I made a mistake here because I need scatter 3 since it's a 3D plot. That's why it didn't work. That looks a little bit better. It's a little bit tough to see that star. Let me make it larger. So we can kind of see it now. It's still pretty small. Try one more enlarging of it so we can see it on our plot. It's fairly large now. So that red star represents our estimated point that used that data cloud. What we can also look at is what are the residuals. So what's the difference between using our estimate and the actual observed data? So I'll store this as res. So that's going to be this A matrix times X. That's our estimates minus our actual observations of B. So in the previous example, we saw that the residual we could get down to 0 when we only had 3 points, but that's going to be pretty much impossible when we have more than 3 points. So here we see the residual. This is the difference between what we estimate their foot size to be and what it actually was, using those original data points, the 1774 data points. So we see that some of them are below, they're negative, some of them are overestimating what the actual foot length is. But what we see is by using this regression, this A/B, the residual is going to be minimized. The plane best fits our data, which means that the residual, or really more specifically the norm of the residual, is going to be at the minimum possible value. This is the plane that makes this as small as it possibly can be. So this is the smallest the norm of the residual can be. The norm we haven't used before, but what the norm does is it takes every element in a vector, squares it, and then adds it together and takes the square root. So it's basically like taking the Pythagorean theorem, but we're using it in multiple dimensions. It's not just x squared plus y squared. We take every element in the residual, square it, sum it together, and take the square root. So that's a measure, the norm is a measurement of how far away from zero we are in general. And it's good because the norm is a scalar value, which means it's going to be compatible with something like f0 or fmin search, and it's something that's easier to minimize than if we look at this long list of residual values. How are we going to tell what's the lowest the residual can be? So the norm is going to help us out there. So any other plane that would be passing through this value, the norm of the residual, is going to be strictly higher